So let's do an overview of buffers. One of the most important equations for buffer is the Henderson-Hasselbalch equation, which is pH equals pKa plus log of base over acid. Now, let's just look at this equation very carefully, and we can see this pH equals pKa. And I want to just show you the similarity and the difference between pH and pKa. When we make them pH and pKa equal to each other, we get protons and as Ka equal to each other. Now, what exactly is H plus? H plus just tells us if we have a solution, it just tells us if the solution is acidic or basic, depending on how much protons we have, right? So pH just gives us a general idea of the solution, but then Ka gives us the strength of the acid. So for example, when we have HF versus HCl, both of them are acidic. They're both acidic in the pH scale. But then the Ka is more specific that tells us that HF is a weaker acid and HCl is a stronger acid because it produces more product of hydronium. Now, I kind of want to expand this idea a little bit further, and let's just do the Ka of HF. So when we do HFKa, remember K is product of a reactant. And when we do product of reactant, we get the hydronium, the base divided by acid. And do you see, guys, it pops up again. The Ka is equal to the proton, which is very similar to the original equation where pH equals pKa. And so I just want to show you this, guys, that these relationship is not random. They're all kind of related. And another reason why I want to show you this Ka of HF is, look, when we do the Ka of HF, we get base over acid, base over acid. And that is how we get base over acid. You see, the Henderson-Hasselbalch equation, it kind of pertains a lot to the proton dissociation, how strong the acid is. And once we find the Ka of the product of the acid, we get base over acid. And so I know the formula is going to be given, but it will be just good to familiarize with yourself this Henderson-Hasselbalch equation. Now, I just want to give you another definition of buffer. A buffer is a weak acid or base, and it's weak conjugate acid and base. And you know, when we see this term, it may look kind of daunting. You see 0.5 of fluoride buffer, and you might ask yourself, what is this? All I want you to think for now is imagine a weak acid and its base equal to 0.5, right? So for example, we could have 0.25 plus 0.25 equals 0.5. Or we can have 0.4 plus 0.1 equals 0.5. And so moving forward, when we talk about buffers, whenever you see a concentration of a buffer of 0.5, just imagine HF plus a base equals 0.5. Okay? The next topic for buffer is buffer range. And the buffer range equation equals pH equals pKa plus or minus 1. And pretty much all this equation tells me is at a certain pH, it cannot be a buffer anymore. And so I'm going to use the example of HF. Actually, I'm going to use the example of HF throughout the whole video. And the Ka of HF is 7.2 times 10 to the negative 4. And when you find the negative log of that is pK equals 3.14. Now, all buffer range tells me once again is for HF, it remains a buffer as long as it remains at 2.14 or it remains at 4.14. But let's just say if the pH goes to 2, is that a buffer for HF? No, because it's outside of this range. And so the buffer range just tells us what pH does that buffer needs to be for it to be a buffer. And the last topic for this overview is buffer capacity. I think this is, it gets kind of confusing, but I think just having a general idea will help you. And so buffer capacity is how many moles of acid or base can I add for it to remain a buffer. And so we're going to use the buffer range of HF that I used from a previous example. And we just want the buffer range to be between 2.14 to 4.14. And so let's just say we have a scenario that we have a buffer of HF and F minus. And I ask you, if I add a certain amount of base, would it still remain a buffer? The way you do that is do mathematically. And so let's just say we add 5 moles of base. And I forgot to mention, this example is when the buffer is ideal, where the base to acid ratio is 1 to 1. So if I add 5 moles of base, right, the log will be 5. Why? Or actually, it should be right over here. Because the buffer was ideal, the base since I add is 5, and the acid will be 1. And so log of 5 is 0.68. Now, is this still a buffer? Yes, because remember, look, since we're adding a base, is 3.14 plus and minus 1. And so since 0.698 is less than 1, it will still remain a buffer. What if I add 7 moles of base? Then it will be log of 7, and it's 0.845. And would it still be a buffer? Yes, because it's still under plus 1. Now, what if I add 11 moles of base? Log of 11 is 1.04. Would it still be a buffer? No, because it's above plus 1. And so what I want to say for this general overview is whenever they ask you, is it still a buffer? Make sure the ratio of base added is log of 10. If it's greater than 10, like log of 11, it cannot be a buffer. And likewise, they could also ask you, is it still a buffer depending on how much acid we add? And so we're gonna do another example. So when I add 5 moles of acid, it's log of 1 over 5. Now, why is it log 1 over 5? Remember how I said base over acid would be ideal, 1 to 1? So base will be the same, but the acid will be 5. Therefore, log of 1 over 5 is negative 0.698. Now, is it still a buffer if I add 5 moles? Yes, because it's still not greater than negative 1. Remember, it's plus and minus 1, right? That's a 1, actually. And if I add 7 moles of acid, it's 0.845. Would it still be a buffer? Yes. And if I add 11 moles of acid, would it be a buffer? No, because you see how it's greater than negative 1? And the biggest takeaway, once again, is when they ask you for buffer capacity, look at the ratio of base to acid or acid to base, right? So for example, if they ask what is the ratio of acid added, the log, it has to be log of 1 over 10. If it's greater than this, then it cannot be a buffer. And therefore, this is just a quick overview of buffer, and then I will make more example problems.